In the last lecture, I mentioned that large number of new molecules have been created by engineers, which are used in various processes, and these molecules have strong absorption bands in the region between 7 micron and 15 micron. Since this is a region where emission for the earth has maximum radiation, these gases, hundreds of these called chlorofluorocarbons, have an impact on climate change, even though they are only in parts per billion. Remember that carbon dioxide at present is above 400 parts per million. These are 1,000 times less concentration, but they do play a role because they happen to be in the region here where earth emits a lot of radiation, and the carbon dioxide absorption band is in the right extreme here. In the region here, not many other gases absorb radiation. So, because other gases do not absorb much, these gases do play a role. Okay. Now, when there is a mixture of gases, life gets a little complicated. If there are two gases A and B in a container, then the transmittance of radiation is a product of these two. Okay. And if you neglect scattering, then transmittance is 1 minus emissivity. So, you can expand this and you see that the total emissivity of the gas is the sum of the emissivity of the two gases minus the overlap between the two gases. Okay. So, these gases here, hundreds of them, which have absorption bands in the region between 7 and 15 micron, they have an impact on climate change. They also have an impact on the ozone layer in the stratosphere. All of you heard of the word ozone hole, and which led to a major international agreement called the Montreal Protocol to cut down the chemicals which cause ozone depletion. Two of the well-known ones are F11 and F12. Chlorofluorocarbons are two of them. These are used widely in refrigerators, and they happen to deplete the stratospheric ozone in a big way, and this was discovered in 1980s, and immediately protocol was signed internationally to prevent the depletion of ozone. And we will talk about this in the next lecture, because although the ozone depletion problem is primarily a problem in chemistry, how these chemicals we have introduced into the atmosphere cause the decline of ozone in the stratosphere. Climate change is caused mainly by carbon dioxide, but the two are connected in two ways. One, some of the chemicals which cause ozone depletion also cause global warming. Okay. And some of the new chemicals which have been discovered which do not cause ozone depletion, but they cause global warming. So, now in any new agreement that we make to contain global warming, we must make sure that the chemicals we are introducing into the atmosphere not only prevent ozone depletion, but also prevent global warming. So, this is a new challenge, and so as a matter of fact, 50-100 years ago, when engineers invented all these new chemicals which did not exist in nature, they were thought of as geniuses because they found chemicals which were inert, non-toxic, non-flammable, and so very useful to use at a household. For example, refrigerator, air conditioner, if it contains a chemical which is highly flammable, it is dangerous or is very toxic. So, many of the new chemicals that were discovered were considered a boon because they did not affect the human beings in that room. But what the engineers did not realize was these chemicals were inert, they did not react, they were not toxic, they were not flammable, although they were the nice properties, but once they leak into the environment and go outside, they remain there for a long time. Okay? Now, if these gases absorb infrared radiation from the earth, we are in trouble, because if they remain on earth for a long time, then they will cause global warming for a long period. Or if they go out and ultimately interact with the ozone layer, that is also bad. So, we have to look at all chemicals which we are now discovering and releasing into the atmosphere in terms of whether they have a long lifetime. If they have a long lifetime, we have to ask whether they are going to deplete the ozone layer or they are going to cause global warming. Both these must be avoided. So, although ozone depletion is a very different problem compared to global warming. Global warming is caused by greenhouse effect. Ozone depletion is caused by chemicals attacking the ozone layer. It so happens some of the chemicals which attack the ozone layer also happen to cause global warming. And now we have discovered some of the new chemicals discovered to prevent ozone depletion cause global warming. So, we need new criteria to permit chemicals to be allowed in the industry, which not only prevent global warming, they also prevent ozone depletion. Okay. Now, before I go to those topics, I want you to understand the complexity of radiation heat transfer. Okay. Here I am showing you the transparent carbon dioxide over a distance of 1 meter in the laboratory, the transmission. Okay. And you can see that the transmission is lowest in the center of the 15 micron band, okay, right here. And as you go away from the center of the band, absorption is not that strong. If you take center of this band and expand it now, enlarge it, this is between 650 and 680. Now, suppose I look at only at 15 centimeter minus 1, just this 5 centimeter minus 1, this particular here, expand it, this one looks like this. Okay. Now, this one looked fairly smooth here, but when I expand, you can see that part of it is not that smooth. There are these little waves. These are rotation lines of carbon dioxide which are overlapping. Okay. Here you do not see much overlap, but here there is an overlap. To show that it is there, I plot the same result with much lower pressure. Okay. This is at Earth's surface, which is 1000 millibar. This is at tropopause at 100 millibar. The same transmission function plotted at a low pressure shows a lot more structure. Why is that? Because as you increase the pressure, these rotational lines start broadening, okay, and they start overlapping each other, and you get this. So, you must appreciate that whenever you see a spectra of any molecule, you have to ask yourself how accurately spectra was measured and whether the resolution is large enough to show individual rotational lines. Okay. If they do not, if they are like this, then when you integrate over wavelength, you might cause some error, because for example, in this case you can see there is strong absorption here, no absorption here, because transmission is 1, again strong absorption here. So, when you integrate, you must take an absorption only at these points, in between there is no absorption. But if your spectra is not that detailed, it is a crude spectra, it will smoothen over all these lines and you will get something like this, which will give you a wrong answer. So, this is a challenge we face in radiation heat transfer in vibration rotation bands, which is that there is a lot of structure to these spectrum, and to get an accurate estimate of greenhouse effect, we need to integrate these with very small changes in wavelength delta lambda, so that we capture the ups and downs of the rotational lines. Okay. At the center of the rotational line there is high absorption, at the wing there is no absorption. Then the next one. So, you have to correctly calculate the absorption at the center and no absorption in the wing of the line. So, that is why all the radiation calculation in climate models is done by specialized codes, which we will not discuss in this course, but they are absolutely essential, because the spectra happens a lot of structure and that structure must be correctly calculated. Again, to highlight that more, I give one more example. This is in a microwave, which is not important for us, but it is good to show the example. This is oxygen which has magnetic dipole moment, which causes rotational transition at high frequencies, 60 gigahertz, and you see this oxygen band at tropopause and the same thing at the surface. Okay. See the difference. At the surface we see no structure of the rotational lines, you see a smooth thing, but in reality if you look at low pressure you see a lot of structure, each is a rotational line. So, this shows that at 1000 millibar the rotational lines are completely smoothened by the presence of nitrogen gas at the ground level, which is not there at 100 millibar. So, this pressure broadening has a important role, and that is why you must remember that although nitrogen and oxygen do not absorb any radiation infrared, by their very presence they alter the width of the rotation lines and thereby affect the greenhouse effect. So, greenhouse effect is influenced by the presence of nitrogen and oxygen indirectly, okay, and we do not talk much about it because the amount of N2 and O2 is not changing in the Earth's atmosphere. But if you want to look at paleoclimate, what happened a billion years ago or 2 billion years ago, when the surface pressure was very different, then you have to worry about the role of N2 and O2 on the greenhouse effect. I will mention it briefly when I talk about paleoclimate. Now, to highlight the complexity of calculating the greenhouse effect, I have shown here a result in which the important 15 micron band of CO2 calculated in various ways. The dashed line is experimental data. The line which is going up and down here, steps, okay, that is the line by line calculation by for the pressure broadening, and the histogram, I am sorry, the line is right here next to the experimental data, this solid line. The histogram is a solid steps function, okay, which is a somewhat crude. See, this is a crude estimate, this is accurate estimate, this is experimental data. What you see clearly is the accurate estimate line by line agrees very closely with the experimental data, but the histogram, which is a quasi random band model, okay, used in the old days 40 years ago, is not that accurate. There are large differences here you can see. Okay. So, today people would prefer to use line by line codes because they are more accurate, but it was not possible 40 years ago because the data was not available in those days. This was work done 46 years ago. So, today these quasi random band models are hardly used for calculating greenhouse effect. Now, to highlight the how important carbon dioxide is, I am showing here the spectra as measured by a satellite outside the Earth's atmosphere of the radiation emitted by the Earth's surface. Okay. Now, the Earth's surface is in this case around 288 Kelvin, okay, somewhere here, and you can see that around the 15 micron carbon dioxide band, the absorption by CO2 is so high that it absorbs almost most of Earth's radiation and re-emits it at a much lower temperature, which is the temperature of the tropopause. Okay. So, the absorption by the 15 micron band is so strong that the radiation that is seen by the satellite is not the radiation emitted by the surface at 288 Kelvin, but by the gases like CO2 and water vapor at around 210-250 degrees Kelvin. So, this shows the huge impact of CO2 absorption band at 15 micron, because it absorbs radiation from the surface, which is at 288 Kelvin, and then it re-emits it at 215 Kelvin. Okay. So, this difference between 288 and 215 is a measure of the greenhouse effect. So, greenhouse effect in this wavelength range is very, very effective, because instead of showing radiation emitted by the Earth's surface, it is only showing radiation emitted by the tropopause. Same thing with ozone. Ozone is here. You can see that ozone absorption band around 9.7 micron. Instead of 288, it is emitting at around 270 Kelvin. It is not as powerful as carbon dioxide, but it is still important. Then look at here around 20 micron, where water vapor absorbs radiation. It absorbs the surface radiation at 288 Kelvin and re-emits it around again 270 Kelvin. Okay, 270 Kelvin. Here also, this is the 6.3 vibration rotation band of water vapor. Here it is taking Earth's surface radiation at 288 Kelvin and re-emitting it around 230 Kelvin. Okay. So, what you see is that the rotation band of water vapor, the vibration rotation band of water vapor here, the vibration rotation band of ozone, the vibration rotation band of carbon dioxide, all of them take the emission from the Earth's surface and re-emit it at much lower temperature, and that is what causes the strong greenhouse effect in the Earth's atmosphere. Okay. So, this shows it very nicely based on satellite data. Okay. Now, for you to appreciate how the emissivity or absorptivity of the gases in the atmosphere depend upon the amount of gas, which is called path length, that is the integral of density of the water vapor from surface to top of the atmosphere. It will be in grams per centimeter squared. Okay. And it varies a whole range depending on what layer you take, and as you go, it goes over a layer of a million times increase. The emissivity goes from 0 to around 100, okay, depending on temperature. Temperature difference is not strong here. So, what you want to notice is the shape of the emissivity curve is not linear. It is linear here, you can in this range convert a linear curve, but it is much steeper here. Okay. So, adding water vapor in this layer will have a different impact than adding water vapor here. Okay. Same thing to our carbon dioxide. Carbon dioxide at very low concentration and path length, the emissivity varies linearly, but as you go up with more and more concentration, the rate of increased emissivity is different. Okay. So, this is very important, and I will show that again in a different context. That is, we add 1 ppm CO2 150 years ago, when the CO2 was 280 ppm, its impact will not be same as today when you have 400 ppm. So, 1 ppm of CO2 added 150 years back and today have a different radiative forcing. Okay. So, it is not a linear function, it is a non-linear function. And for you to appreciate the effect of greenhouse gases in Sahara and in Antarctica, I have shown two different spectra measured by satellites. Okay. Very accurate measurement by satellites, very high resolution. You see in Sahara the dramatic impact of CO2 at 15 micron. Sahara temperature is around, I would say, 330 degrees Kelvin, that is 50 degrees centigrade. Okay? And from there the radiation is absorbed and then re-emitted at around 215 Kelvin, similar to the last example. So, carbon dioxide has a strong greenhouse effect because it absorbs radiation from the surface of Sahara at around 325 Kelvin and re-emits it at about 215 Kelvin. Same thing with the ozone layer, same thing with water vapor, and at two different regions here. Now, let us come back to from Sahara to Antarctica. Antarctica, the shape looks very different. Here you see a depression in the emission curve where ozone and water vapor is there, but here you see an increase. This should puzzle all of you. Why is the curve different in Sahara compared to Antarctica? That is because Antarctica has a temperature inversion. Antarctica has long cold nights during the winter. So, you will find in Antarctica the layers near the ground from the surface to around 2 or 3 kilometers, the temperature will not decrease with height, but increase with height. Okay? This is a special feature of the polar regions, both Arctic and Antarctic. They have strong inversion because they have a strong radiative cooling by the surface during the long polar nights. Okay? Because of the inversion, the carbon dioxide at higher layers emits more than the surface. The surface of Antarctica is at around 180 Kelvin, okay, while a 2 kilometer high layer is more like 200 Kelvin. So, what you are seeing here is that CO2 is able to emit better at a higher level at the surface. So, the greenhouse effect in Antarctica will be negative. That is, because of the increase in CO2 in Antarctica, CO2 will be able to emit more radiation in Antarctica than without CO2. So, this is a consequence of the inversion layer, and I will talk about this in more detail when I look at several models to show why if the temperature of the atmosphere is higher than the surface, the greenhouse effect has an opposite sign. Okay? So, this must be very well understood to appreciate the role of temperature lapse rate in the Earth's atmosphere. Okay? Now, here I am comparing the transpiration spectra of the Earth as measured by satellite from space to the surface, from space to 11 kilometers. I want to focus the layer where water vapor absorbs. You see that from space to the surface, there is almost no transmission of radiation in the 20 to 100 micron region where water vapor absorbs very strongly through rotational bands. Now, if we do not go to surface but go only to 11 kilometers close to tropopause, you see transmission is not 0. It is more like 0.5. So, this shows that a strong absorption by water vapor in the rotation band occurs only in the layer 0 to 11 kilometers. Above 11 kilometers, absorption much less, okay, because most of the water vapor is between this is the wrong statement. Most of the water vapor is from the surface to 11 kilometers. Above 11 kilometers, water vapor is very small in the stratosphere. Okay. So, absorption occurs only in the troposphere. Now, I want you to look at what is called radiative efficiency. Radiative efficiency is the measure of how much additional greenhouse effect occurs if you add 1 more ppm by volume of a given gas. Okay. So, here I have compared adding 1 ppm CO2 at 278 ppm and 1 ppm of CO2 at 364. You see that the greenhouse effect is not same, 0.029 and 0.0158. So, greenhouse effect is less when CO2 is more than when CO2 was less. Okay. So, this is because of the non-linear relationship between greenhouse effect and the amount of the gas. Okay. So you must remember that the greenhouse effect is sensitive to what is the amount of greenhouse gas present at that time. Okay. So you look at pre-industrial condition today, CO2 amount is different. So when you add 1 ppm today and when you add 1 ppm 115 years ago, the effects are different. Okay. Now remember that the last about now 40 years, there were losses of ozone in the stratosphere. Okay. So that caused negative radiative forcing, because ozone was lost, greenhouse effect was less. Okay. So that must be kept in mind. And the second thing in this particular table is the lifetime. Lifetime is very important in the future climate mitigation scenarios, because if you have a gas like carbon tetrafluoride CF4, okay, whose greenhouse effect is quite large, but lifetime is 50,000 years. It is a very stable gas. Okay. Now that means whatever you release today will remain in the atmosphere forever. So you have to worry about it because it has a strong greenhouse effect. Although the amount of carbon tetrafluoride will be measured in parts per trillion, not parts per million, but still, because it is there for a long time, you have to worry about its long term consequence. So this point will be discussed a little later in this course. Okay. Now before I go on to that, I want you to understand the importance of carbon dioxide. Carbon dioxide is the most important gas in the Earth's atmosphere because it is there for a long time. Its lifetime is hundreds or even 1,000 years. And if you look at whatever data we have measured about the carbon dioxide concentration in the last 50 million years, okay, 50 million years ago there was time when Earth had 2000 ppm of CO2, and during the last glacial maximum it was around 200 ppm, and it has varied in between. Okay. And you look at the global mean temperature measured through proxies, they are almost linearly related. So this shows that in a long time scale we are talking about not 5 years, 10 years, 100 years, we are talking about millions of years. The Earth's global mean temperature was controlled primarily by carbon dioxide. Okay. Water vapor played a role, but the major role was played by carbon dioxide, because carbon dioxide determines the temperature. If the temperature was low, then water vapor effects are lower, because if temperature is low, water vapor is also low. Okay. When the temperature was high, as it was 50 million years ago, water vapor would have played a very important role. Okay. So remember that CO2 is the controlling gas in the Earth's atmosphere because it doesn't condense, and it determines the global mean temperature, which determines the greenhouse effect of water vapor. So you must remember that CO2 is the most important gas in the atmosphere, although its concentration is lower than that of water vapor. Okay. So this is somewhat puzzling to many people, but you must remember this from the point of view of the lifetime of the gas. Gas has a long lifetime, while the lifetime of water vapor is 1 week. Okay. Within 1 week, water vapor is condensed out. Now the nonlinear effect of the concentration on greenhouse effect is best shown by measuring the change in intensity in a layer of gas as you increase the concentration. Okay. Initially it will be linear, then as the CO2 increases it becomes logarithmic. Okay. Why? Initially concentration low, most of the absorption takes place in the center of the line where the absorption is very strong, but as the concentration increased, the center of the line gets saturated, then now the absorption takes place in the wing of the line where the absorption is weaker, and so the increase in greenhouse effect is slower. Okay. So if you look at gases like chlorofluorocarbons, which are in parts per trillion, they are in this regime mostly, while Carbon dioxide is mostly in this regime, logarithmic regime, because concentration is much higher. So, we will later on see when you have formula for radiative forcing for carbon dioxide and water vapor, carbon dioxide and chlorofluorocarbon, you will find we will use a logarithmic form of the formula for carbon dioxide, but we will use a linear form for chlorofluorocarbon, and this is because of the difference in concentration. Chlorofluorocarbons are in parts per trillion, carbon dioxide in parts per million. It makes a big difference. Now, here is an example of the abundance of various gases in the atmosphere in 1750 and in 1998. Okay. In 1750, we have a rough idea about the concentration of CO2, methane, nitrous oxide and carbon tetrafluoride. These are measured through air trapped in gas bubbles in the ice core taken out of Antarctica. Okay. These are very, very accurate measurement made in the laboratory after the ice core was retrieved and brought to the lab, and you carefully take the gas sample from the bubble and measure the various concentration. Okay. And you find that the concentration of the gases in 1998 was much higher than it was in 1750. Carbon dioxide was more than double. Nitrous oxide went up by around 40 parts per billion. So, methane and nitrous oxide measured in parts per billion, CO2 measured in parts per million, and all the other gases are measured in parts per trillion. Okay. Rest, okay, all the other gases. So, but realize that there are this gas is parts per million, then others are parts per billion, and these are parts per trillion. Still, all of them are important because these have a long lifetime, while methane lifetime is very short, that of these other gases are very, very long. So, impact of a gas on Earth's climate depends not only on how strong the absorption band is, also how long it remains in the atmosphere. Okay. So, to characterize this quantity, we define a quantity called climate warming potential, which I will take up in the next lecture.